Hello, class. Today we're going to learn about power. There are three equations you need to know for calculating power. The one equation is already boxed below. P equals IV. And P will stand for power. The other two equations are derived from using Ohm's law. Please also write down P equals I square R and P equals V square over R. You will use one of these three equations to solve for power, and the unit for power is watt, capital W. For our first example, we want to calculate the resistance of a 40-watt automobile headlight designed for 12 volts. The best power equation to use is V squared over R. We can then rearrange the equation to solve for resistance. And from there, it's just a plug and chug to get 3.6 ohms. What you pay on your electric bill is not power, but energy. The power consumption multiplied by time. And we have been measuring energy in joules, but the electric company measures it in kilowatts hour, or kWh. To get kilowatt hours, just convert your watts to kilowatts, and then multiply that number by how many hours the power was used for. We'll do an example next. An electric heater draws a steady 15 amps on a 120 volt line. How much power does it require and how much does it cost per month? We'll say about 30 days if it operates for 3 hours per day. And the electric company will charge 9.2 cents per kilowatt hour. To calculate power, we'll use this equation, P equals IV. Just plug and chug to get 1800 watts. The next step is to convert watts to kilowatts. Now we have to calculate how many hours the power was used for. So 3 hours per day for 30 days is a total of 90 hours. The last step to get kilowatts is to multiply your kilowatts by the hour used to get 162 kilowatt per hour, or kilowatt hour. Now to figure out the cost, it's 9.2 cents for every kilowatt hour. So just multiply 162 kilowatt by 9.2 cents to get 1,490 cents. Or about $15 for the cost to run a heater for about 3 hours a day for 1 month. Now the wires used in homes to carry electricity have a very low resistance. However, if current is high enough, the power will increase and the wires can become hot and start a fire. To avoid this, we use fuses or circuit breakers, which disconnect the circuit when it goes above a predetermined value. Fuses are one-time use devices, and if they blow, the fuse is destroyed and must be replaced. Here are some images below of what fuses look like. Circuit breakers, which are now more common in homes than they once were, are switches that will open if the current's too high. They can also be reset, which is better than buying a new fuse. The figure B to the left is everything's okay. But then the figure to C to the right means the circuit is open because too much current went through it and it bent that by a metallic strip. Now all you have to do to reset it is just push down that switch. Here's an example. We want to determine the total current drawn by all the devices in the current below. We'll use P equals IV for all these devices. Rearrange it to solve for current. And then plug and chug for all 5 devices. To obtain the total current, we just add the current from each device, and we get 29.8 amps. Now if the current is designed for a 20 amp fuse, the fuse should blow to prevent an overload with the wires from getting too hot and starting a fire. Next example. Let's say your 1800 watt portable electrical heater is too far away from your desk to warm your feet, and cord is too short, so you plug it in into an extension cord rated at 11 amps. Why is this dangerous? Well, according to the power equation, the electric heater draws 15 amps of current. The wires in the extension cord is rated at 11 amps and could become hot enough to melt the insulation and cause a fire. A couple of terms I want to expose you now is direct versus alternating current. Current from batteries flow in a steady in one direction, and we call this direct current, or DC. The current only flows in one direction. All of our problems that we'll deal with will be direct current. Now, current from a power plant or your wall outlet varies sinusoidally, meaning the direction switches back and forth. In a closed loop, it would look like the current switches from counterclockwise to clockwise, then back again. This is called alternating current, or AC. Most of our devices have a converter to switch from AC to DC because our electronics only use direct current. Later on, we'll see why it's more efficient to deliver AC, or alternating current, to our homes.